All right, so last time we left off talking about integration by parts. And I mentioned this problem before we left last time to the extent that I told you that not all the problems in this section require U substitution. And actually, Emily came by and talked to me about one of the problems because she'd started the section already where she encountered that. They don't all require integration by parts. They could use U substitution. Let me clarify. And this happens to be one of those problems. So if you take a look at this one, we have x times the square root of x minus 5. So the two methods that we've looked at, I guess you could say, when we have products are U substitution, and you did that back in Calc 1, and we've used it lots since then, and integration by parts, which is the section that this is in. So we tend to do something when we see square roots like letting the value underneath the square root be U. That's kind of one of those standard tricks that we try. And it may not always work, but it's a good thing that we try, right? Everybody with me? Okay. The reason that we like to let what's underneath the square root be U is because then I end up with an integral, an integral where we have got a square root, but there's only underneath the square root instead of an addition and subtraction underneath the square root. So it's much easier to work with U to the 1/2 than it is to work with x minus 5 to the 1/2. Is everybody tracking with me? Okay. So if this is U, what is du? It's dx, or 1 dx if you prefer. And that works just fine with understanding that this piece right here is the square root of U, right? All this right here is square root of U. The problem is that little x on the outside, what does it go with? Because it doesn't go with the dx because my du is not x dx, right? Well, this is one of those ones, and we've seen this process before, where we take the description for U and we rewrite it in terms of x. So we would add 5 to both sides, and we would find out that U plus 5 equals x. And you might say, well, how does that help? Well, the reason that that's more helpful is because that puts the addition and subtraction outside of the square root instead of under the square root, because under the square root causes problems. Okay? So I can rewrite then this as the integral of U plus 5 and then the square root of U du. Right there. And then if I want to think about this U right here as U to the 1/2, right, then I can say that when I distribute this, I can combine the U and the U to the 1/2 to be U to the what power? 3 halves. Plus 5U to the 1/2 du. Is that okay? Everybody sees where the pieces came from. Now, that's just power rules, right? So what's the antiderivative of U to the 3/5? I don't know why it says 3/5. It should say 3 halves. Let's fix that. Oh, because I was looking at the 5 that came next. Okay. It's fixed now. So what's the antiderivative of U to the 3 halves? Right, I increase the power by 1, makes the new power 5 halves, and then I divide by the new power 5 halves, which is just as multiplying by 2/5. The next one, I've got the 5 already, but now what's the antiderivative of U to the 1/2? This is audience participation time. U to the 1/2 becomes what? Very good, thank you. 2/3 and U to the 3 halves. And then today, every time you do this, you're going to remember to write down something else, right? Plus C, because it needs to be on there because we're doing an indefinite integral. No numbers at the top and bottom. All right, so let me clean this up just a little bit. I have 2/5 U to the 5 halves plus 10/3 U to the 3 halves plus C. Am I done? What's missing? Right, I started the problem in terms of x. I need to end the problem in terms of x. So I'm going to need a little more space. Move over a little bit. Here's my 2/5. u is x minus 5. So this is x minus 5 to the 5 halves plus, and then we have 10 thirds, and you have x minus 5 to the 3 halves, and then plus c.
Do you want us to put the plus c right after you take the antiderivative, or can we wait till the end to put it on?
Technically, it should come right after you do the antiderivative. As long as it's going to be a part of your answer, I'm not going to be too persnickety about it, but very technically, yes, it should be right at this point right here. I have some students who will sometimes sort of equate that if I remove the du and the integral sign, then I insert the plus c. So those are happening simultaneously. One removes and the other one inserts. And that's actually the proper thinking on the matter. So yeah, it'd be better if you put it in right there. Okay. All right, ready for the next one? So that was not integration by parts, right? U substitution was powerful enough for that one. All right, I have one more, and I realized after I did it, I don't know if when I did your notes if I fixed it or not. I don't think I did because I'm seeing it. This is actually a definite integral, and my directions could have indicated that, so I changed the directions when I wrote them out there. So we're going to find the definite integral. Definite integral means it has limits on top and bottom, right? So there aren't going to be any plus c's on this one right here because I'm going to evaluate them at 1 and 0. Now, this particular one, though, is one that doesn't look like a product, does it? It doesn't really look like we have something with x in it times something else with x in it. But it is integration by parts, and the reason it's integration by parts is because you've got a natural log. And you don't have any way of taking a form of a natural log and taking its antiderivative yet. Okay? So integration by parts is going to be necessary. So you might think, well, but again, I don't have parts, so what am I going to do? Well, let's take a look. We're going to start by identifying that u is the natural log of 4 plus x squared. And we will have a du of that in a moment. We'll come back to there in just a sec. I'm supposed to be able to fill in a dv and then take an antiderivative to get a v. What is left to let dv equal? Dx. So it doesn't look like a function, but it is. It's in essence 1 dx, right? And what's the antiderivative of 1 dx? It's x. So if it helps you to see it, put it in there. This is a 1 here, 1 dx. So the antiderivative of 1 is x. Now we're ready to go back to the natural log part to do the derivative part. So what is the derivative of natural log of 4 plus x squared?
2x squared over 4 plus x squared.
Okay, so the natural log part gives me the 4 plus x squared that you mentioned, right? And then the part that you mentioned first was the derivative of the inside, correct? So the derivative of the inside isn't quite 2x squared, but it is 2x. So you can either write that on top, or you could write it times 2x at the end. Either way would be fine. And then I need dx as a part of that. Okay, so is everybody with me on that? All right. Now, that lets me take these pieces and combine them the way we did last time. So if you remember, the way we were combining last time is the first thing you do is you do u times v. So u times v on this one is x times the natural log of 4 plus x squared. That's uv. And then we do the other diagonal right here. And when we look at that diagonal, we do v du. So this is minus an integral. This integral is still 0 to 1, but if you leave them off for the moment because you're going to have to evaluate at the end, it's okay. As you're working, you're going to have to do the evaluation, and don't forget that part. But so if you take a look at this now, I've got 2x squared because I have the 2x that's on top, and I have it multiplied by the x that's over there, what v is, right? Is that okay? All right. And then this is over 4 plus x squared dx. So what am I going to do with that? Because I'm telling you what, that doesn't look especially pretty.
You're going to divide.
I am. How do you know I'm going to have to divide, Cameron?
Same powers.
Yeah, so if your exponent on top is the same as the exponent on bottom, or if it's bigger than the exponent on bottom, that's long division. Okay? So the same powers gives it away, I guess you could say. So we're going to take 2x squared, and that's going to be divided by, and I'm going to rewrite it so the x squared's in front, but this is x squared plus 4. So we'll write in a 0x and a 0 in here. So what am I going to multiply x squared by to get 2x squared? 2. 2 times x squared is the 2x squared that I thought I was going to get. And then I have 2 times 4, which is 8. Thank you. And I didn't end up actually needing the linear x term in the middle there. And then I need to subtract these, right? So these cancel out, which was the whole point. And then I end up with negative 8 at the bottom. So this actually results in a quotient of 2. The remainder is 8 over the divisor, which is x squared plus 4. So when I'm going back with my problem, this right here is going to replace this right here. Those are equivalent quantities. Okay, so I'm going to go to the next screen and try and recopy all of this information. So I have x natural log of 4 plus x squared. And then I had minus the integral of 2 minus 8 over either x squared plus 4 or 4 plus x squared is fine. And then dx. Okay, is that all right? Did I miss any pieces? No? Okay. All right, so the x ln 4 plus x squared stays. Now, what's the antiderivative of minus? Well, I've got the minus. Then what's the antiderivative of 2? 2x. Now, we could either distribute the negative right now or I'll distribute it in a minute, which should be fine. That's what I'm going to handle with it. That's how I'm going to handle it. But what does the second one here become? What do you do with 8 over x squared plus 4? Do you remember, Nidra? What's that? We are separating the integrals. We did the first piece already. That's the 2x part. Now I'm looking at the integral for the second piece. So what will the integral for that second piece be? That's right. It's the arctangent. Do you guys remember those arctrig functions? Mm-hmm. This one's arctangent. That's the one we need. So the 8 doesn't get affected. But then I have arctangent, and somebody's going to have to look it up for us to remember all the pieces. Because it is arctangent, but it's got some ratio in it, and we maybe have a ratio that's going to affect my 8 in front and all that stuff too. So somebody take a look when you did your arctrig functions on your derivatives sheet. It's x over a, and did we write down what x and a are? Not yet, so let's do that. So x is x in this problem, right? Okay, so our x is x. What is a in this problem? 2. Now, when you told me x over a, Hannah, you meant right here, right? Was there anything else over a? Was there a division by a in the front or anything? Okay, so right in front here, move this a little bit so I have some more space. Right in front here, I have a 1 over a, and a is 2 in this problem. And I changed that. I said it and didn't do it. So this is x over 2. And then normally, right, we would put plus c here, but we're not going to in this problem because I had a definite integral, the 0 and the 1, that I'm going to have to go back to in a moment. But
Where's there the 1/2 again?
The 1/2 came from the formula for arctangent.
Okay.
It has a 1 over a in the front, and our a is 2.
Oh, okay.
Yes. No, that's okay. So those pieces in red actually came from that tangent formula. All right, so right now I've got x times the natural log of 4 plus x squared. And then I have minus 2x. Then I have plus, and I've got 8 times 1/2, which is, of course, 4. Arctangent of x halves. And now I'm going to evaluate all of this at 1 and at 0. And we do have to be careful here because this isn't a linear, or this isn't a polynomial function, so I don't necessarily know that if I plug in 0, I'm getting 0 everywhere. Polynomials do that, right? Quadratics, cubics, those kinds of things. But arctangent, arcsine, those kind of functions don't necessarily. So we do have to be a little bit careful when we're working with them. All right, the number 1's really nice, though. So I've got 1 times the natural log of 4 plus 1 squared, which would be 5, minus 2 times 1, which would be 2, plus 4 arctangent of 1/2. Does that look okay to everybody? All right, so all of this will be subtracting. Now, the first piece is 0 because I have 0 times natural log whatever, so that one's 0. The second piece is also 0 because it's 2 times 0. So the part that I do need to be cautious for is the 4 arctangent of, well, 0, right? Because it's 0 over 2. Okay, so this is natural log of 5 minus 2. And 4 arctangent of 1/2. Well, arctangent of 1/2 is not on the unit circle. It's not one that you have an angle for because it would actually mean that the sine and the cosine have a ratio where one of them is twice the other one. That's what the 1/2 would mean because tangent is a sine over cosine ratio. And none of your unit circle values have that property. Okay. The unit circle values for tangent that are ones you should sort of have in your mind are as if you had an arctangent of 1. Those are the 45-degree angles, right, the pi over 4s. If you had an arctangent of -1, same thing. And then if you had an arctangent that had the square root of 3's in them, either 1 over square root of 3 or square root of 3 over 1, either of those would be arctangent values you know. But arctangent of 1/2 is not one of the ones from our unit circles, so there isn't a closed, definite form that we have to work with. All that to say, you get to leave it. You don't have to find a simplification for it, okay? So 4 arctangent of 1/2. The other portion that we have is 4 arctangent of 0. Now, arctangent of 0 is the unit circle value. Do you know what the arctangent of 0 is? It is 0. Remember, tangent is sine over cosine. So in essence, you want sine over cosine to be equal to 0. And that happens for sine when sine is 0. And sine is 0 at an angle of 0. If it said arc cotangent of 0, that would not be 0. It would actually be at the 90-degree angle at the top, which is pi over 2. So it's not just always 0 because this has a 0 in it. That's not what's going on. So you have to think about that unit circle. So this actually is 0 in this particular problem. So all of this is 0, which means my solution is this piece right here. Now, how could you check to make sure you did it right? Because this does not look like a number if you just look at it, right? What could you do? Okay, so I could put this expression in my calculator, right? And this expression in my calculator would spit back out at me some kind of a decimal approximation, right? How am I going to check to make sure that decimal worked? Exactly, with the original one, right, Hannah? So I could take my original expression with the natural log 4 plus x squared, and I could put it into my calculator. And then I could do that integrate feature that the calculator has, because it will do it with numbers, right? 0 to 1. That's the nice thing about definite integrals. They're more work, pencil and paper, because you have to do the plugging in at the end, but you have the ability to check your work when you're done, because you have the ability to plug the numbers in, and this calculator will do for you. So we actually could check to make sure that the decimal approximations were the same, right? Any questions on this one? Okay, so when you see a natural log in an integration by parts, natural log is always going to be which piece? U. Natural log is always going to be U. Okay? All right. All right, let's go ahead and take a look